Hello, and welcome back to another video. This is the last video in the series where we are looking at the four main ingredients for severe weather. The previous videos looked at lift, moisture, and instability. This video will discuss wind shear. So what role does wind shear play in a severe weather? Wind shear increases the organization and lifespan of a severe thunderstorm. It is defined by the change in wind direction and speed with height. If you enjoy this video and the series as a whole, leave a like and subscribe, and we'll get started. So before we talk about wind shear, I want to discuss how we measure the environmental winds. Most wind measurements and meteorology are measured in knots. I imagine most of you are more familiar with miles per hour, so here's how to convert. You'll take your wind measurement in knots and multiply it by 1.15, and that'll give you your wind measurement in miles per hour. I don't believe you'll see meters per second on this channel, but in case we do come across it, what you'll do is you'll just multiply it by 2, and you'll get your wind measurement in knots. And so next, I want to talk about the wind barbs on the right side of your screen. These show the wind speed and the direction that the wind is coming from on that given level. And so, how do we know what the speed is at that given level? So we look at the flags here. The longer flags, for example, represent 10 knots that you see here. And then the shorter flag here represents 5 knots. And so you just add them up together, and that is your wind measurement. So for example, this would be 25 knots. And then on the bottom here, you see the little pennant on the end. That is 50 knots. That represents 50 knot winds. And so that covers up our environmental winds and how we measure them. So now we're going to look at wind shear. As we know, we're looking at the changes in wind speed and direction. What effect does this have on a thunderstorm? The National Weather Service has a graphic to help illustrate this, and these arrows on the right side indicate the increasing wind speeds. As they increase, the winds will tilt the updraft inside a thunderstorm, and the precipitation will fall away from the updraft and will not contaminate the warm inflow into the storm. Unlike what you see on the left side, where the precipitation is falling directly onto the updraft inside the storm. And so that is going to interfere with the warm inflow that the thunderstorm needs to survive. And so when you have wind shear, that'll tilt this updraft and the precipitation will fall away from it and will not interfere with the warm inflow. And so that this increases the life cycle of the thunderstorm and makes for a more organized structure. There are a few different layers that we'll use to diagnose the wind shear. And a common term you'll hear on this channel is deep layer shear. And this looks at the change in wind speed from the surface to 6 kilometers up. And this is measured in knots. So what is the source of this wind shear? The main one is a strong mid-level jet at 500 millibars. And this results from a strong trough at 500 millibars that's approaching from the west. And so your winds would be flowing from the base of that trough and into the target region. And so that's where our deep layer shear comes from. Not only does wind shear affect the life cycle of a thunderstorm in intensity, it also influences what type of storm we'll get, aka the storm mode. There are 4 main modes of severe storms, and those are pulse, multicell, linear, discrete, or semi-discrete supercells. I also have written down the wind shear values that are usually associated with these modes. So I'll go through them. Our pulse type storm, these are single cell thunderstorms that are usually come from the summer pop-ups that are typically your hit or miss summer afternoon thunderstorms that just randomly pop up as a result from the heat of the day. And these storms are usually not severe, but occasionally they can produce microburst winds of up to 58 miles per hour. And so the wind shear that's associated with them is usually less than 20 knots. Multi-cell storms, these are single-cell thunderstorms that are in really close proximity to each other. So they're so-called multiple cells associated with them. And these require just a little bit more organization and some modest wind shear that ranges typically from 20 to 30 knots. And then we have our linear storm mode, So this is like our squall line, which is can either be a solid squall line or kind of a broken line of storms. And so this requires a little bit more organization in our storm structure. And so typically the wind shear values associated with it is greater than 30 knots. And then we have our supercell mode. And these supercells are rotating or thunderstorms with organized rotating updrafts. And these are responsible for all modes of severe weather, including tornadoes. And these require a lot of organization and some stronger wind shear to work with. And so the wind shear values associated with these are typically greater than 40 knots. And so the last thing I want to talk about on deep layer wind shear is our shear vectors. And I'm going to use our case study from March 31st to help illustrate this. So I'm going to go and look at 1 p.m. from this event. And this is showing the deep layer shear that is contoured over the target region from the Midwest, such as like Illinois and Iowa, down into the deep South. And so our shear vectors are also plotted, which show the magnitude of the deep layer shear and the direction that the shear is coming from. And so this helps determine the storm mode, particularly distinguishing between a linear versus a discrete storm mode. And so what we have to do is figure out what our initiating boundary was for our storms. And in this case, this was a prefrontal trough that is located from Missouri down into Arkansas. And so you'll take our initiating boundary, which is about here, and then we'll draw our shear vector at each given location. And so up and down this initiating boundary, these were what the shear vectors were like with respect to that initiating boundary. And so if our shear vector is parallel to our initiating boundary, that's going to indicate a linear storm mode. And when it's perpendicular to our boundary, it's going to be discrete. So up and down this initiating boundary, you had our shear vectors mostly perpendicular to our boundary, with maybe getting a little bit more of a parallel up in Iowa. So the storms may initially be discrete, but they would quickly transition into a line, which is exactly what happened. And then further south, where the shear vectors were more perpendicular to our initiating boundary, they remained discrete for a much longer period of time. And so that is going to wrap up our discussion on deep layer shear. And so now let's go discuss another critical layer for wind shear. This layer ranges between the lowest kilometer and up to 0 to 3 kilometers, and this is where we diagnose the low-level wind shear, which is critical in forecasting, particularly for tornadoes. Recall back on the video on moisture, where we talked about the low-level jet and that it develops around 1 or 2 kilometers. This plays two main roles in a severe weather threat. In that video, we saw that it transports heat and moisture. And the other role that the low-level jet plays is that it strengthens the low-level wind shear. And a southerly low-level jet, generally greater than 35 to 40 knots, makes the environment more favorable for tornadoes. And so I'll show you what the low-level jet looked like back on this day. Let me zoom out here a little bit. And so look at 850 millibars. And so we'll go back to 1 p.m. and our time of interest. And so this is what our low-level jet looked like. Basically we had a 40-knot flow, basically from the Gulf Coast up through Alabama and up to the Midwest, is where you had a very strong low-level jet that, one, it transported the heat and moisture necessary for thunderstorms, but it also created really strong low-level wind shear across this region. And so that's why the environment was so favorable for tornadoes. And as we recall, this was the result from this day. This is the preliminary reports from this event, and there's a lot of tornado reports. These are all the tornado reports that occurred from that day. 163 tornadoes were reported from that day. So very prolific tornado event. And then that is largely related due to the low-level jet and just the amount of moisture we were transporting up into the region. And so that covers up uh, our low-level shear and deep layer shear. And I'm going to wrap up this video by looking at one more sounding from March 31st. And this is looking at the environment at Lincoln, Illinois from at 7 p.m. And mainly I'm going to focus on the hodograph and the environmental winds. So we can see the change in wind speed and direction with height by looking at the wind staff. So I'll demonstrate this for you. So our surface winds are almost straight out of the south here. And then we have our winds at 1 kilometer, which is basically our low-level jet. That's out of the south-southwest. And then we have our winds at 6 kilometers, which are basically straight out of the southwest. And so this change in wind direction from east to west is called a veering wind profile. And another way to visualize this wind shear is by looking at the hodograph. And I believe I went over this in a different video in understanding Skew-Ts and soundings, but I'll go ahead and review on how we construct the hodograph. So what the hodograph does is it takes each wind data point and it basically connects all the dots. So we'll look at the surface. We have a surface wind of about 20 knots. That's almost straight out of the south, not quite, but pretty much straight southerly. And so that is where our surface wind is. And so each point here is the level, is the kilometer that it's looking at. So then next we'll look at 1 kilometer. If I find my marker again, okay. And so we have wind at 1 kilometer out of the south-southwest at around 50 knots. And then at 6 kilometers, you have the wind out of the southwest at around 80 knots. And so what this creates is a large looping hodograph that looks like this. And this type of hodograph is the most favorable for tornadic supercells. And so another parameter that we commonly use in meteorology is called storm relative helicity, or SRH for short. And so what this is looking at is the tendency for your winds to move in a helical flow like this. It's not the best demonstration, but you'll get the idea. And so the larger your hodograph is, and the more curvature you have in your hodograph, the more SRH you're going to have. And these values are found down here in this table. And so these are a couple of different layers that we can look at. The most useful layer is going to be this effective inflow layer. And so basically this just takes into account your low-level wind stability. And so do we have a supercell, or do we have a thunderstorm that has a rotating updraft? And so if we do, this is the number that's going to be most useful, layer that's going to be most useful. And so numbers that are generally over 200 units are going to be more favorable for tornadoes. And once you get values that are in the 300 or 400 range, that's when you can start considering potential for significant tornadoes. And so also just an FYI, this right here is our deep layer shear, and surface is a 6 kilometer wind shear, and so that's at 63 knots in this case, and so that's pretty favorable wind shear for supercells. And so that's going to cover it for this video and for this series. I hope you enjoyed it and learned something. And so after these videos go up, I'm going to start getting onto a more regular schedule for uploading videos, and I'll see you then.